Greetings. Welcome to week 8, and today we'll be discussing two questions. First would be on the state space, and second would be on frequency response. So, today in first question, we have been given a second order system which is governed by this uh, ODE. We have to find how many state variables are required for representing this second order system in the state space form. We have to find the state matrix, we have to find eigenvalues of the state matrix obtained, find the input vector of the state space realization, find the output vector of the state space realization, and we have to then find out the transfer function using a conversion from state space. Let's discuss a few things about state space form. The transfer function form is unique, whereas the state space form is not unique. That means we can represent the same system by different kind of state space forms. So these are also called as canonical forms for state space representation. So there are several like like observer canonical form or controller canonical form. Each of these give allows you to simplify and understand things in one aspect or the other. So let's get right into this question. First, we have this governing equation. So y double dot of t plus 5 into y dot of t plus 6y of t is equals to u of t. Now, since this is a second order system, we require two states. So the order of the system is equal to number of states are required to represent that system in state space form. So what do we do? We'll define x1 as one state, which will be y of t. Then if we differentiate this, x dot 1 of t will be y dot of t. So let us define this x dot as x2 of t. All right. So and if we use these definitions and we plug it into the equation, which is this, so this y double dot of t would be x2 dot of t, and we have already defined this y dot of t to be x uh, sorry so let's differentiate it again. We have y double dot of t, which is x1 double dot of t, which is x2 dot of t. All right, so we know we have substituted y double dot of t. Now we will substitute y dot of t to be let's say x1 dot of t plus 6 y of t. So y of t was x1 of t is equals to u of t. So if you uh, remember from the class, state space representations are of the form x dot of t equals to ax of t plus bu of t and y of t is equals to c into x of t plus d into u of t. So these are the two equations which define state space. So we can also replace this x dot 1 as x2 of t, so that we can write x dot on one side and everything else in the form of x and u on the other side. So our equation, this equation can be written as x2 dot of t is equals to u of t minus 5x2 of t minus 6x1 of t. And we already have x1 dot of t as x2 of t. So if we were to write things in matrix form, that is x1 of t and x2 of t, so the derivative of these two equals to some matrix which was A into x1 of t and x2 of t plus some other matrix into u of t. So let's write this equation here. So x1 dot is 0 times x1 plus 1 times x2 and 0 times u of t. Now the second equation is this one. So x2 dot is 1 times u of t minus 5 times x2 and minus 6 times x1. So uh, let me use this to be the vector symbol, right? So x dot of t is equals to a into x of t plus b into u of t. So u in this case is a scalar. So a matrix is 0, 1, minus 6 and minus 5. And b is a vector 0, 1. So now this is the state matrix we have found, which is A, and we have let's also, for sake of completeness, write y of t. Y of t was what? Y of t is x1 of t. So x1 and x2. So this is 1 and this is 0. And the D matrix which we have here in the general form is essentially 0 because there is no u of t term in it. So the C matrix would be 1, 0 and D would be 0. So this expression or this is called the state equation, and this is called measurement equation. All right. So uh, we have converted the given system into a state space representation. And we have also found out this input vector, which is B. Now we want to find the eigenvalues of the state matrix obtained. So the state matrix we have obtained is A, and we want to find its eigenvalues. So how do we do that? We write we take A minus I lambda, take its determinant and set it to 0, and then we solve for lambda, which are the eigenvalues. But before jumping into that, let us quickly, uh, in a perspective, try to intuitively understand what eigenvalue is. So, if you have a matrix A, and if you can write an expression like an equation like this, AB equals to lambda V, then we are looking at two entities here, this particular V and this lambda. Okay, so there is a special vector V, which when it is transformed using the matrix A remains the retains its direction but gets scaled by lambda. So let's try to write it. So for a given transformation matrix A, there are certain vectors that when transformed using matrix A uh, retains its directions and uh, is scaled by a factor. So these certain vectors and this factor is what we are looking at. So these vectors are called eigenvectors, and this factor is called eigenvalue. So the eigenvalues are uh, preserved under transformation. So if you have any kind of similarity transform applied to this matrix A, then the eigenvalues of the transformed matrix would also be the same. So now that we have little more perspective on eigenvalues, let's see how do we calculate that. So we have to take the determinant of A minus lambda I, where I is the identity matrix of size A. So we have 0, 1, minus 6 and minus 5 minus lambda times I, which is 1, 0, 0, 1. So if I take the determinant, that will be lambda in bracket lambda plus 5 minus 1 into minus 6. So that would be lambda square plus 5 lambda plus 6. So and then we have to set this to 0. So we have to solve this polynomial. So lambda's value which would solve this would be lambda plus 2 and lambda plus 3 is equals to 0. That means lambda is equals to minus 2 or lambda is equals to minus 3. So let us keep a note of it. These are the eigenvalues. What is so special about these eigenvalues? We'll take a look at it very shortly. So let's look at the next portions. Yeah, the output vector is essentially vector C, which we found as 0 and 1 comma 0. Now next we are supposed to figure out the transfer function and using the state space realization. So the transfer function is given by C in bracket Si minus A inverse B plus D. So in our case, B is 0, C is 1 comma 0, and A we just wrote here, and B is 0 1. So first let's write Si minus A and take its inverse. So so we have S minus 1, 6 and S plus 5. Now if we were to take its inverse, we have to divide by the determinant. So S in bracket S plus 5, 6 into minus 1, and there is already a minus sign, so it is plus 6 into, we interchange the diagonal terms, S plus 5 and S, and we put a negative sign on the cross diagonal term, so it will be 1 and minus 6. So if we solve this into S plus 5, 1 minus 6 and S. So what we look at in the denominator here is actually the same equation we wrote, which was the characteristic polynomial for this matrix A. So let's plug it into the transfer function. equation. So this is 1 over s square plus 5s plus 6 is a scalar. So let me take it out because it is the determinant. So, and then let's write C, which is 1 0. Then the rest of the matrix from this Si minus A inverse. Then B is 0 1, and D was 0 anyway. So let's do these matrix multiplications. So I'll reserve this 1 0, and let's multiply this term with this term. So s plus 5 into 0, s plus 5 into 0, that is 0, plus 1 into 1, that is 1. Then we have minus 6 into 0 and plus s into 1, that would be s. So after multiplying in the uh, these two vectors, we'll get 1 into 1, that is 1, plus 0 into s. So overall this will be 1. So our transfer function g of s comes out to be, now let's write poles of this. So s is equals to uh, s square plus 5s plus 6 equals to 0. That means s plus 2 and s plus 3 equals to 0. This implies poles are s equals to minus 2 and s is equals to minus 3. So let's highlight this. So if we take a look at poles, and if we take a look at eigenvalues of matrix A, they are essentially the same quantities. So let's make a note here somewhere. Let's use red. Poles of a transfer function are the eigenvalues of state matrix. So if eigenvalues of A, all of them, are negative, that means in left half of the complex plane, then the system is stable. Alright, so let's review. We have answered this also using the relationship between transfer function and state space realization. Calculate the transfer function of the system. So what is the benefit of using a transfer function? Uh, or rather, why do we even discuss the state space if transfer function essentially talks about the same system? We do that because here in transfer function, the relationship is only between input and output, right? So g of s is y of s by u of s. However, when we are writing the state space, we are looking at two different variables here, x1 and x2. So when we are looking at state space representation, it brings out certain hidden variables or hidden nodes in the system. and that can give us better understanding in terms of which hidden variable is resulting into the instability of the system. For example, if in this particular case we would have started with a system which has one of the poles in the right half of the complex plane, that means one of the eigenvalues of the state equation, sorry, one of the eigenvalues of state matrix A would have been positive. And in that case, we would have figured out which state, either x1 or x2, causes the instability. And then specific controllers might be designed in order to take advantage of that. So we can stabilize that one unstable point or unstable node. Right. So now let's move on to the second question. So where we have been given a transfer function of a plant, and this question corresponds to the sinusoidal or frequency response. We have to find magnitude and phase of this. So let me write this plant transfer function as P of S. P of S is equals to S plus 2 and S plus 4. To find frequency response, we take S is equals to J omega. Alright, so substituting S equals to J omega, we get P of J omega. So we have been asked about the magnitude and phase of this at angular frequency of 1 radian per second. So substituting omega equals to 1, so let's multiply this by J minus 4, or we can straight up take the magnitudes. Alright, so we have been asked the magnitudes. Let's substitute J equals omega equals to 1, J plus 2 and J plus 4. So if we take magnitude of P of J, rather P of J omega at omega equals to 1, this would be square root of 1 square plus 2 square divided by square root of 1 square plus 4 square. So this would be whole under root 5 by 17. It comes out to be 0.542. Now let's also calculate angle of P of J omega at omega equals to 1. This would be angle of J plus 2 minus angle of J plus 4. So we take tan inverse 1 by 2 minus tan inverse 1 by 4. So if we plug this into calculator, this turns out to be 12.528 degrees. So now we have been asked find the ratio of magnitude of the sinusoidal transfer function at angular frequency of 10 radian per second to that of 1 radian per second. We have already figured out this at 1 radian. Now let's do the same for at omega equals to 10. So we have to take magnitude of uh, 10j plus 2 divided by 10j plus 4. This will be 10 square plus 2 square. So if we take the ratio E of j omega, this would be 0.947 divided by 0.542, that is 1.747. So what we see that what we can see here is that the magnitude uh, at omega equals to 10 would be 1.747 times higher than the magnitude at omega equals to 1. So that brings us to the end of second question. We have some more time left, so I think we can have some more discussion. Uh, what do you say?
Yeah, so yeah, can you scroll a bit down?
Yeah, sure.
The eigenvalues. Yeah, yeah, the green bit.
Yep.
So, wait. Scroll a bit up where you write about the eigenvalues and
Ah,
eigenvectors.
the note.
Yeah.
No, scroll up. The green one. All right.
This one. Yeah. So
Okay.
here, if I'm right, eigenvectors are certain unique states, right? Uh, uh, above in the above vector in the above state space representation. Your x is basically your eigenvector, right?
Sorry. So no, x is not my eigenvector. X is my state.
X is your state, but
Yeah.
here when you write a times x,
Ah,
a times the b thing which you wrote there,
yeah.
definition of eigen values.
Right.
So can you tell that your x is also x also has certain eigenvalues?
No, no, no. See, eigenvectors are defined for a matrix, and to be more precise, it should be a square matrix. Okay.
Okay.
So, what we are saying is there are these transformation matrices A.
Hmm.
So, if you multiply any, uh, say you have a matrix, let's go to a new page on a discussion. So, you have a matrix A. Okay.
Right.
And you have a vector X.
Hmm.
So, let's say your X is like this. Okay.
Okay.
And if you do A into X, okay, your vector now starts looking like this. This is AX. Okay.
Okay.
So, This is this was your original vector.
Hmm.
This is transformation
Right.
using A. So if we take a 2D analogy, what does a transformation A does is it do it does
Scales and
two,
rotates, no?
yeah, scales and rotates,
Okay.
right? So we are saying that there are certain vectors V, right, which corresponds to A, that only scales and does not rotate.
Fine, fine. I got that. Okay.
Hmm.
So what I was asking is,
Okay.
when you defined your state space equation on top,
Mhm. Okay.
you spoke about eigenvalues for the state transition matrix, right? A.
Okay.
Yeah. So in essence, if you apply the same definition there, your x corresponds to this x over here, right?
Uh,
Your
no.
vector x1
Okay.
and x2
Mhm.
corresponds to the same x over here, right? If you apply the same definition there.
Can you clarify? I did not understand your
Okay.
question.
Wait. So can you scroll up? Keep scrolling up till you reach that.
This, sorry, one more.
More. Okay. Yeah. So here you wrote x1 dot of t, x2 dot of t is equal to a times x1 x2 t, right?
Right.
Yeah. So here you spoke about the eigenvalues of the A matrix, right?
Right.
So I'm asking if your eigenvectors
Uh-huh.
can be some, uh, some vector in the form of x1 and x2.
Okay, let me say it the other way.
Okay.
You can certainly
Basically,
write.
I'm asking if you can explain the definition of eigenvalues and eigenvectors using this state space representation.
mm, uh, okay, I don't know if I can explain using the state space notion or not.
Okay.
But eigenvalues and eigenvector is more of a general concept, and it originates from the matrix rather than the state space representation, right?
Okay.
Okay, so it is more fundamental in that regard. So going from state space to eigenvalues, eigenvector is something I don't think we should be doing.
Okay.
However, we can come from the idea or definition of eigenvalue and eigenvector,
Hmm.
and then uh, you know link it to the notion of state space. So what the state space is saying is you are writing x dot equals to ax plus bu. That means you are saying how does the x change. Okay, that is what you are defining with the state equation
Hmm.
written here. So what are you saying? The state changes and it depends on two things. What my state is at current point,
Hmm.
okay, and what my input was given. And the contribution of input is determined by B,
Yeah.
okay. And your A, which is your state matrix, determines how your state gets transformed at each time instance. So when we actually write this into a discrete form, as we know, uh, xk plus 1 equals to ax plus bu, there every time your A matrix would do something to your state,
Hmm.
your input would add, your input would also contribute, and that would result in the next state of your matrix, right? Sorry, next state of your system.
Yeah. Yeah. Yeah.
All right.
Right.
So I hope at least in intuition you are clear about the eigenvalues.
Yeah. 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 Yeah.
Right. You can always refer to Gilbert-Strang for formal definition.
Okay.
And one more thing is there is subtle difference uh, between eigenvalues and singular values. So apart from mathematical definitions, If you look in the context which we have encountered eigenvalues in our uh, idea of systems theory or controls, is that we are using square matrices to map the state onto its evolution, right?
Right,
So
right,
if you're mapping the same quantity on itself or its evolution, then you are bound to use square matrices, and hence, we discuss about eigenvalues. But when we are going from one quantity to some other quantity, right? So, for example, if we take a simple, uh, two tank system where you are giving in some flow, the two tanks are connected and it's giving some outflow. So the states which are H1 and H2, say two heights of water in the tank, are mapped to the flow output flow rate, which is Y. So here we are looking at different quantities, that is, the states are mapped onto measurements. So in such a case, we would be looking at, that is, if need may, we would be looking at singular values, because this matrix is certainly not square.
right,
They are not required to be. But when you are mapping from, say, one state onto itself, then of course you will end up looking at square matrices. So yeah, subtle difference. I would
okay,
encourage you to take a look at modern control theory for these things.
okay. And one more thing, you briefly mentioned
Mhm.
about how eigenvalues can tell you which state is causing instability, right?
Yeah.
Yeah, I just zoned out during that. But can you just briefly tell that again?
Yes. So in transfer function, if we look, right, let's write down the transfer function for this. It is s square plus 5s plus 6.
Hmm.
Right. So what does a transfer function do for you? It maps, it maps your inputs to your outputs, right?
Hmm.
But when you're writing it in state space form, we are interested in certain additional variables, like say x1 or x2. Okay.
Yeah.
So x1 is essentially y, but x2 is something which is different, that is y dot. Okay. Uh, so you are now looking at certain hidden quantities called states. They may be equal to measurement, they may be some transformation of the measurement, or something entirely different, right? And even something which you may not be able to measure. So if we take again the classic two tank example, which has inflow measured and outflow measured and nothing else, your hidden variables are the heights, say h1 and h2. Now these hidden variables h1 and h2, if you are writing it in state space form, you suddenly start getting understanding of how much of the tank is full, right? So that is one significant advantage state space provides. It allows you to take a look at quantities which would have been hidden in the representation of states of transfer function. So yes, I think that's what I was trying to mention. And when you take a look at the eigenvalues of state matrix, so say, uh, all right, let me write something here, x1 dot x2 dot. So let us write autonomous system. It does not have any input. Okay.
Yeah.
And your eigenvalues are, say, 1 and uh, say minus 2. Okay. So if you can try solving for this, your eigenvalues would be the diagonal terms here.
Okay, yeah.
Okay, so what you are saying is your x1 dot would remain the same,
Hmm.
right, as x1,
Yeah.
but your x2 dot, sorry, so this, if you write it in the equation form,
Okay.
x1 dot
Is
is
equal to
equals to x1,
yeah.
and x2 dot is equals to minus of x2, minus 2 times x2. Okay, so here, since you have a negative, uh, right, minus x2, this would uh, this would be a stable system, right? What will be the solution of this? E power minus 2t. Okay,
Yeah.
x2 of t. But what will be the solution here? It would be e power t,
Right.
which is unstable.
Uh,
So it will blow up to infinity.
yeah, yeah, yeah.
Okay, but if you were to write this as a transfer function, how would you write it? S minus 1 and s plus 2, right?
Yeah.
So the transfer function does not tell you anything about which node of these uh, different states
Yeah.
or which state is unstable, but state space allows you to take a look at it.
Okay.
All right,
Yeah,
so
yeah. Got it.
got it, great. So that's one benefit of why we look at state space.
Okay.
Another notion is of discretization, which you can learn in advanced courses on controls, like modern control theory, where if you write this into a discrete time format, it allows you to it allows easy implementation on computers, right, which is xk plus 1 equals to ax plus bu kind of format.
Yeah, yeah.
All right, so any further questions?
No, no, that's it. Thank you.
All right, great. So thank you for joining. I hope this was helpful.